Welcome to the Pure 3 crash course. We'll start with algebra, so without further ado, let's dive right in. Number 1, part A. Sketch the graph of y equals the modulus of x minus 2. Okay, so to do that, we start by sketching the graph of y equals x minus 2. This is a straight line, so that means we need 2 points that lie on this line to be able to sketch it. Okay, so let's find the coordinates when x equals 0. So when x is equal to 0, y is equal to 0 minus 2, so y is equal to negative 2. So we have a set of coordinates that is 0 minus 2. And then we need another set of coordinates. So when y is equal to 0, we get 0 is equal to x minus 2. So x is equal to 2. So we get the point 2, 0. Now let's use these 2 points to sketch the graph of y equals x minus 2. Alright, so let's draw a Cartesian plane. This will be our y-axis, and then this will be our x-axis. So let's start with the point 0, negative 2. So 0 is here, that's our origin over here, and then negative 2 would be here. This is negative 2, so the point is over here. And then we have another point at 2, 0. So if we count 2 units in our x-axis, that's 1, that's 2. 2 would be over here, so our second point would be here. Let's see if we can extend our graph down here. Alright, so we're drawing a line through these 2 points. Okay, so I'm going to draw the part below the x-axis in gray, which I'll explain in a bit. So that's drawing the line through these 2 points. And then blue for the rest of the graph. Okay, so this is the graph of y equals x minus 2. Now we want the graph of y equals modulus of x minus 2. So we know that the modulus is always positive, so that means that this part that I've drawn in gray has to be reflected in the x-axis. So we then go ahead to reflect this part. So we know that it passes through 0 minus 2, which means that it must pass through 0 2 if we reflect it. So that would look something like that. Let me try to get it passing through 0 2. So like that. Close enough. So this will be y is equal to negative x minus 2. And then we'd erase the gray part because that's not part of our graph. So make sure you label both arms, and this is what makes up the graph of y equals modulus of x minus 2, and this will be our final answer for part A. Part B, solve the inequality. The modulus of x minus 2 is less than 3x minus 4. Okay, so to solve this inequality, you can tell that the first part is our modulus graph, and then the second part is a straight line 3x minus 4. So let's draw this straight line 3x minus 4, y equals 3x minus 4 on the same plane. And since this is a straight line, we need 2 points that lie on the line. So we'll start with when x equals 0, and that gives us negative 4. So that will be 0, negative 4. And then we need another point. So we use when x equals 1. That will be 3 times 1 minus 4. So you get y is equal to minus 1. So that means we have the point 1, negative 1. So let's start with 0, negative 4. 0, negative 4 will be down here. 1, negative 1, negative 2, negative 3, negative 4. 0, negative 4 is this point over here. and then we have the point 1, -1. So 1 is here, -1 would be there. So this is the point, and then we are drawing our line through these points to look something like that. And this is the line of y is equal to 3x minus 4. Okay. So to be able to solve our inequality, we first need to find the point of intersection, the x coordinate at the point of intersection. So this is our point of intersection, and we can tell that it's this line and this line that are intersecting. So we can equate them together to solve our point of intersection. So that would be negative x minus 2. That's this expression over here, and this is equal to 3x minus 4. 3x minus 4. So let's solve that equation that we have. So if we expand our brackets here, that's negative x plus 2 is equal to 3x minus 4. Let's put the terms with x on the same side. So 3x plus x is equal to 2 plus 4. So 4x is equal to 6. Divide both sides by 4. You get x is equal to 3 over 2. So what that means is that this point of intersection here is 3 over 2. So now that we have the point of intersection, we now have to find the region that they are looking for, or the region that is satisfied by our inequality. So it's saying the modulus graph is less than the line. That means we want the region where the modulus graph is below the line. So this less than sign is telling us below the line. So let's look either side of the point 3 over 2. So if we take, for example, this point over here, we can tell that at this point, the modulus graph is above the line. But if you go to the right side of 3 over 2, you can tell that at this point, the modulus is actually below the line. So what this tells us is that to the right of 3 over 2 is the region that satisfies our inequality. So that means x is greater than 3 over 2 would be our solution, and that would be our final answer. Find the quotient and remainder when 2x to the power 4 plus 1 is divided by x squared minus x plus 2. Okay, so that's x squared minus x plus 2. And we've got 2x to the 4 plus 1. So we're going to say x squared into 2x to the 4. That gives us 2x squared minus, multiply this 2x squared by our divisor over here. So that's 2x squared times x squared. That gives us 2x to the 4. 2x squared times minus x. That gives us negative 2x cubed. And then that's 2x squared times 2. That gives us plus 4x squared. And so if we simplify 2x to the 4 minus 2x to the 4, that becomes 0. And then we've got negative 2x cubed, which becomes positive 2x cubed. And we've got negative 4x squared, so that's negative 4x squared. And then let's bring down that 1, that's plus 1. Then we're going to say x squared into 2x cubed, so that gives us a positive 2x. Minus, let's multiply this 2x by our divisor. So that's 2x times x squared. That gives us 2x cubed. 2x times negative x. That's negative 2x squared. And then 2x times 2. That gives us 4x. And let's simplify. So 2x cubed minus 2x cubed. That gives us 0. Negative 4x squared plus 2x squared. That gives us negative 2x squared, and then we've got negative 4x, so that's negative 4x, and then we have this one plus 1. Okay, and now we're going to say x squared into negative 2x squared, and that gives us negative 2. And let's multiply this negative 2 by our divisor. So that's negative 2 times x squared, that's negative 2x squared. Negative 2 times negative x, that gives us positive 2x, and then negative 2 times 2, that gives us negative 4. And if we simplify, negative 2x squared minus 2x squared gives us 0, then negative 4x minus 2x gives us negative 6x, and then 1 minus 4 gives us plus 5. And now we can tell that the highest power in our divisor is now larger than the highest power in our dividend. So we stop here and we can conclude that our quotient is what you have on top here. That's 2x squared plus 2x minus 2. And then our remainder is over here, negative 6x plus 5, and this is our final answer. The polynomial ax cubed plus x squared plus bx plus 3 is denoted by p of x. It is given that p of x is divisible by 2x minus 1, and that when p of x is divided by x plus 2, the remainder is 5. Find the values of a and b. So we're given that p of x is divisible by 2x minus 1. So using the factor theorem, this means that p of half is equal to 0. So basically whatever makes the bracket 2x minus 1 equal to 0. So if you solve for x here, you'd get x is equal to 1 over 2, and that is the value that we use here. And then we are told that p of x is divided by x plus 2, and the remainder is 5. So again, what makes the bracket 0, x plus 2 equals 0? You'd end up with x is equal to negative 2. So we can conclude that p of negative 2 is equal to the remainder using the remainder theorem. Now let's go into substitute into our equation. So we'll start with p of half is equal to 0. So substitute x with half, so that becomes half cubed plus half squared plus b times 1 over 2 plus 3, and this is all equal to 0. So half cubed will give us 1 over 8a plus half squared, which is a quarter, plus half b plus 3 equals 0. Then we've got 1 over 8a plus half b, then we have a quarter plus 3. Let's punch that into a calculator. 3 plus a quarter, and that gives us 13 over 4. So that's plus 13 over 4. This is equal to 0. Let's multiply it through by 8 to get rid of all our denominators. So that becomes a, and then that becomes 8 over 2b, which is 4b, plus that becomes 8 over 4 times 13, which is 2 times 13. So that's 26, and this is equal to 0. Now let's evaluate p of negative 2 is equal to 5. So we're going to substitute x with negative 2. So that's plus negative 2 squared plus b times negative 2 plus 3, and this is all equal to 5. Negative 2 cubed is negative 8, so that's negative 8a plus 2 squared, which is 4, minus 2b plus 3, and this is equal to 5. So negative 8a, negative 2b, 4 plus 3, that's plus 7. Let's bring this 5 to the left-hand side, so that's minus 5. And this is now equal to 0. So that's negative 8a minus 2b plus 7 minus 5, which is 2. And this is all equal to 0. Now you notice that we have two equations in terms of a and b. We can solve these two equations simultaneously to evaluate a and b. So let's make a the subject of the formula in our first equation. So that becomes negative 4b, negative 26. We can substitute it into our second equation. So that's negative 8a, we'll substitute a with negative 4b, negative 26, minus 2b plus 2, and this is equal to 0. If we expand, we have negative 8 times negative 4b, which gives us 32b. Then we have negative 8 times negative 26. If you punch that into your calculator, you get 208. So this is plus 208 minus 2b plus 2 is equal to 0. So we've got 32b minus 2b. That gives us 30b. Then we have 208 plus 2. That gives us 200. And this is all equal to 0. So 30b is equal to negative 210. Divide both sides by 30. And you get b is equal to, let's punch this into a calculator, 210 divided by 30. So we end up with b is equal to negative 7. Now let's evaluate a. A is equal to negative 4b, which is negative 7, minus 26. So a is equal to, if we punch this into a calculator, that's negative 4 times negative 7 minus 26. We get a is equal to 2. Therefore, we can conclude that a is equal to 2 and b is equal to negative 7. And this would be our final answer. Part A. Expand 2 minus 3x to the negative 2 in ascending powers of x up to and including the term in x squared, simplifying the coefficients. Okay, so we've got 2 minus 3x to the minus 2. So we use the formula for binomial expansion when n is rational or when n is negative. And for that to work, we first have to make this value over here 1. So we're going to do that by factoring out that 2. So this becomes 2. 1 minus 3 over 2x. And this is all to the power negative 2. Then now we're going to distribute the power negative 2 since these are multiplying. So it becomes 2 to the negative 2 times 1 minus 3 over 2x to the negative 2. And if we simplify this, that's 1 over 2 squared, which is a quarter, times 1 minus 3 over 2x to the power negative 2. And now we can use the formula for binomial expansion when n is rational. So we have our 1 over here, and then negative 3 over 2x will represent x. So this becomes a quarter. Then let's open up big square bracket. Then we've got a 1 plus n, which is negative 2, times x, which in our case is negative 3 over 2x, plus n, which is negative 2, n minus 1, and this is over 2 factorial multiplied by x, which is negative 3 over 2x, and this should be squared. And let's close that bracket. Now let's simplify our coefficients. So we have a quarter, and that's 1. Then we've got minus 2 times negative 3 over 2x. That gives us a positive 3x. And then for the coefficient of x squared, let's punch that into the calculator. That's negative 2 times negative 2 minus 1 over 2 factorial multiplied by, that's negative 3 over 2 to the power 2. And that gives us 27 over 4. And the x will be squared. Now let's multiply through by a quarter. So that's a quarter plus 3 quarter x plus 27 over 16 x squared. And this will be the expansion of 2 minus 3x to the power negative 2 up to and including the term in x squared. Now part B says that we should state the set of values for which the expansion is valid. So when you're using the formula for binomial expansion, that's 1 plus x to the power n. It states that the modulus of x should be less than 1, or in other words, x should be between negative 1 and 1. So in this case, the value of x that we use is negative 3 over 2x. So that should also be between negative 1 and 1. So we'll then say negative 3 over 2x should be between negative 1 and 1. So we're going to multiply through by negative 2 over 3 to make x the subject of our inequality. So if we do that, you end up with negative 2/3, and you end up with 2/3 over here, which you can also write as the modulus of x is less than 2/3, and this would be our final answer for part B. Express 4x squared minus 13x plus 13 over 2x minus 1 times x minus 3 in partial fractions. Okay, so the first step when dealing with partial fractions is to determine whether our fraction is an improper fraction or a proper fraction. And to do that, we're going to compare the highest powers in both the numerator and the denominator. Now, in our numerator, we can clearly see that our highest power is 2. And then in our denominator, if we were to expand, you notice that we have a quadratic. So that would mean the highest power is also 2. So since the highest powers are equal, we have an improper fraction. And for an improper fraction, we'll start by expanding our denominator. So this becomes 4x squared minus 13x plus 13. And if we expand our denominator, we get 2x squared minus 6x minus x, which is minus 7x, and minus 3 times minus 1, which is positive 3. And the next step would be to rewrite our numerator in terms of our denominator. So we're just going to start by writing our denominator as our numerator for now. And this is over 2x squared minus 7x plus 3. Now what we want to do, we want to make this numerator that we have equal to the numerator that you have on the left hand side. And we're going to start by looking at the coefficient of x squared. In this case, we have a 2, but we want to get to 4. So we're going to do that by multiplying the whole expression here by 2. So when you then say 2 times 2, you get the 4 that we have on the left hand side. Now you notice that that then affects the other terms. So it affects the term in x and the term independent of x. So we need to fix that. On the left hand side, we have negative 13x. But if we were to expand on the right hand side, we have 2 times negative 7x, and that gives us negative 14x. So we want to get, so we have negative 14x, and then we want to get to negative 13x. So that means we have to add x, because negative 14x plus x gives you negative 13x. So we're going to add that x outside the bracket. Then now for the term independent of x, we have 13 on the left hand side, and then we have 2 times 3 on the right hand side, which is 6. So we have 6, and we're trying to get to 13. That means we have to add 7, because 6 plus 7 gives us 13. So we add the 7 outside the bracket. Okay, and now what we're going to do is we're going to distribute our denominator. So this becomes 2 times 2x squared minus 7x plus 3, and this is all over 2x squared minus 7x plus 3 plus everything that's outside the bracket, x plus 7 over our denominator, that's 2x squared minus 7x plus 3. And now you notice that this will cancel out, and we have the constant 2 over there. So this becomes 2 plus x plus 7 over 2x squared minus 7x plus 3. And now you notice that on this term, the highest power in the denominator is higher than the highest power in the numerator. So that means our fraction is now a proper fraction, and we can now decompose into partial fractions as usual. And to do that, we're going to write this as x plus 7. Let's ignore the 2 for now. And then we're going to go back to the expansion of the denominator. So that's 2x minus 1, x minus 3. So that's the expansion of this quadratic over here. And now we're going to decompose it into partial fractions. So we're going to say a over this bracket 2x minus 1 plus b over the other bracket, that's x minus 3. Then multiply both sides by this denominator to get rid of all the denominators. So we end up with x plus 7 is equal to a times x minus 3 plus b times 2x minus 1. Now we need to evaluate a and b. So let's start by evaluating b. To be able to evaluate b, we need to find a value of x that will make this bracket equal to 0. So if we say let x equal 3, this bracket over here will end up being 0, and when it's multiplied by a, it means this whole term is then cancelled out. And now we only have 3, that's the x there, 3 plus 7 is equal to b times 2x minus 1, b times 2 times 3 minus 1. So that's 3 plus 7, which is 10, is equal to 2 times 3, that's 6, minus 1, that's 5. So 5b, divide both sides by 5, you get b is equal to 2. And now we need to evaluate a. So we need to find the value of x that will make this bracket equal to 0 so that we cancel out the term in b. And that value of x would be half. So let x equal half. And let's substitute x with half. So this becomes 1 over 2 plus 7 is equal to, that's a, open bracket, half minus 3. And half plus 7 gives us 15 over 2. And this is equal to half minus 3, which is negative 5 over 2a. Multiply both sides by negative 2 over 5, you get a is equal to, let's punch that into the calculator, that's 15 over 2 times negative 2 over 5, and we get a is negative 3. So now that we have our values of a and b, we can come back to this expression over here and substitute a and b. So we know that a is negative 3, so that becomes negative 3 over 2x minus 1, and b is 2, so that becomes 2 over x minus 3. Now let's not forget the constant that we got at the beginning, so it means our final answer will be 2 minus 3 over 2x minus 1 plus 2 over x minus 3. This is how we decompose into partial fractions, and that's it for our algebra video. You can now go on to do the topical past paper questions, and when you're done with them, you can move on to the next video. Bye-bye. Welcome to the logarithm section of our Pure 3 crash course. Let's get into it. Solve the equation ln 3 plus ln 2x plus 5 is equal to 2 ln x plus 2. Okay, so let's write that down. That's ln 3 plus ln 2x plus 5, and this is equal to 2 ln x plus 2. Let's start by combining the logarithms on the left hand side using the laws of logarithms. So since they're adding, this becomes 3 times 2x plus 5, and this is equal to, and then let's bring this 2 up using laws of logarithms again. So that's ln, this will be x plus 2 squared. Let's simplify. We have ln, that's 3 times 2x, so that's 6x plus 15, and this is equal to ln x plus 2 squared. Now let's apply the exponential function to both sides to get rid of the ln. So that would become 6x plus 15 is equal to x plus 2 squared. Let's expand the quadratic that we have on the right hand side. So that's x squared plus 4x plus 4. Let's put everything on one side. We have x squared plus 4x minus 6x plus 4 minus 15, and this is equal to 0. So x squared minus, that's 4x minus 6x, that's minus 2x. Then we have 4 minus 15, which is minus 11, and this is equal to 0. And now let's use the quadratic formula to solve our quadratic equation. So x is equal to minus b, so that's minus minus 2, which is 2 plus or minus the square root of 2 squared minus 4, a is 1, and c is negative 11, and this is all over 2 times a is 1. So x is equal to, let's punch this into our calculator, that's 2 plus the square root of 2 squared minus 4 times 1 times negative 11, and this is all over 2 times 1. This gives us 1 plus or minus 2 root 3. So if we separate the solutions, that's x equals 1 plus 2 root 3, and x is equal to 1 minus 2 root 3. Now we know that the lim function does not take values of x that are negative, so let's substitute this value into our original equation to see if it satisfies the equation. So that would be ln 3 plus ln 2x. In this case, x is 1 minus 2 root 3, and this is plus 5, and this should be equal to 2 ln, that's x, which is 1 minus 2 root 3 plus 2. Okay, so if you substitute the right hand side into your calculator, you end up with an error because the value in the brackets simplifies here to give us a negative value, and we know that ln function does not take negative value, and therefore we're going to disregard our negative solution here. So we can conclude that therefore x is equal to 1 plus 2 root 3, and this would be our final answer. Solve the equation ln e to the 2x plus 3 is equal to 2x plus ln 3. Okay, let's start by putting everything with ln on one side, ln e to the 2x plus 3, and then we're going to move this ln 3 to the left hand side, so that becomes minus ln 3, and this is equal to 2x. Using laws of logarithms, these two logarithms will combine to give us ln e to the 2x plus 3 over 3, and this is equal to 2x. And then we're going to apply the exponential function on both sides to get rid of this ln. So this becomes e to the 2x plus 3 over 3, and this is equal to e to the 2x since we've applied the exponential function on both sides. Now multiply through by 3 to get rid of our denominator here. That's e to the 2x plus 3 is equal to 3 e to the 2x. So that becomes 3e to the 2x. Move this to the right hand side, so that's minus e to the 2x, and this is all equal to 3. So you get 2e to the 2x is equal to 3. Divide both sides by 2, e to the 2x is equal to 3 over 2. And then apply the ln function on both sides to get rid of this exponential. So that becomes 2x is equal to ln 3 over 2, and then multiply both sides by half to make x the subject of the formula. So x is half ln 3 over 2. And now let's check, do they want us to give our answers an exact value? They want it correct to 3 decimal places. So let's punch that into a calculator. 1 over 2 ln 3 over 2, and that gives us x is equal to 0.203 correct to 3 decimal places, and that will be our final answer. Okay, so let's look at this question on linear law. The variables x and y satisfy the equation x to the n y squared is equal to c, where n and c are constants. The graph of ln y against ln x as a straight line passing through the points 0.31, 1.21, and 1.06, 0.91 is shown in the diagram. Find the value of n and the value of c correct to 2 decimal places. So we are given this equation that the variables x and y satisfy. This is linear law, so that means we have to reduce this equation to a linear form. So that's x to the n y squared is equal to c. Apply the natural logarithm to both sides. So that's ln x to the n y squared is equal to ln c. So this becomes ln x to the n plus ln y squared is equal to ln c. That should be a c. And then let's bring down the powers. So that's n ln x plus 2 ln y is equal to ln c. Now let's make ln y the subject of the formula. So that's 2 ln y is equal to negative n ln x plus ln c, and divide through by 2. So ln y is equal to negative half n ln x plus half ln c. Okay, so if we compare this to the equation of a straight line, you will notice some similarities. Y equals mx plus c. So in this case, we are given that our graph here is of ln y against ln x. So notice how this ln y would be the same as y, and then this negative half n would be the same as m, and since it's against ln x, this ln x is representing the x over here, and then the half ln c would be representing this c over here. So we want to evaluate n. What we can use is that we can tell that m negative half n is representing m. So if we can find the gradient of the line that we're given here, we can find n. So let's start by finding the gradient m using the coordinates that we have been given here and here. So that's change in y. So 1.21 minus 0.91, and this is over that's 0.31 minus 1.06. Let's punch this into a calculator. 1.21 minus 0.91 over 0.31 minus 1.06, and that gives us negative 0.4. And we said m is equal to negative half n. Okay, so we can say that negative half n is equal to negative 0.4. So multiply both sides by a negative 2, you get n is equal to negative 0.4 by negative 2. That gives us 0.80. So that's n, and now we have to evaluate c. And to do that, we're going to use the equation that we reduced into linear form. So that's ln y is equal to negative half n ln x plus half ln c. And we're going to use a set of coordinates. So let's use this set. And remember that our graph is ln y against ln x. Ln y against ln x. It's not the graph of y against x. So this point over here, this 0.31 represents ln x, and 1.21 represents ln y. So be careful when you're substituting here. So we're saying that ln y is 1.21 is equal to, and we know that negative half n is equal to negative 0.4. So that's negative 0.4 times ln x, which is 0.31, 0.31 plus what we're looking for, half ln c. Okay, so this is 1.21 is equal to, we've got negative 0.4 times 0.31, and this gives us negative 0.124 plus half ln c. And now our goal is to make c the subject of the formula. So half ln c is equal to 1.21 plus 0.124, and this gives us 1.334. Let's multiply both sides by 2. So that becomes ln C is equal to 1.334 times 2. That is 2.668. Apply the exponential function to both sides. So that C is equal to e to the 2.668. Punch this into the calculator. That's e to the 2.668. And that gives us 14.41, correct to 2 decimal places, and we can conclude that therefore n is equal to 0.80 and c is equal to 14.41, and this would be our final answer. So that's it for the logarithms video. You can now go on to the topical questions. See you in the next video. Welcome to the trig section of this Pure 3 crash course. Let's get straight into it. Express the equation tan theta plus 60 degrees is equal to 2 plus tan 60 degrees minus theta as a quadratic equation in tan theta, and hence solve the equation for theta is between 0 degrees and 180 degrees. Okay, so we're given tan theta plus 60 degrees, and this is equal to 2 plus tan 60 degrees minus theta. So let's use the compound angle formula for tan theta that's available in the MF19. So this would become tan theta plus tan 60 degrees over 1 minus tan theta tan 60 degrees, and this is equal to 2 plus, we'll also expand this using the compound angle formula. So that's tan theta, or rather tan 60 degrees minus tan theta, and this is all over 1 plus tan 60 degrees tan theta. And now let's evaluate tan 60 degrees using our calculator. Make sure you're in degrees. Tan 60 is equal to root 3. So we can simplify this to become tan theta plus root 3 over 1 minus root 3 tan theta. And this is equal to 2 plus root 3 minus tan theta all over 1 plus root 3 tan theta. Okay. And now let's get rid of our denominators. So that means we're going to be multiplying through by 1 minus root 3 tan theta, 1 plus root 3 tan theta. Okay, so if we multiply by that, here we end up with tan theta plus root 3 multiplied by 1 plus root 3 tan theta, and this is equal to 2 times 1 minus root 3 tan theta times 1 plus root 3 tan theta, and then our last term will become plus root 3 minus tan theta, and that's multiplied by 1 minus root 3 tan theta. Now let's expand. So we've got tan theta times root 3 tan theta. That's root 3 tan squared theta. Then we have tan theta times 1, which gives us plus tan theta. Then we've got 3 tan theta times root 3. So that gives us 3 tan theta. And then finally we have root 3 times 1. That gives us root 3. So this becomes 2. And notice that this is a difference of two squares. 1 minus root 3 tan theta times 1 plus root 3 tan theta. So that simply becomes 1 minus 3 tan squared theta. And then let's expand this. So we've got negative tan theta times negative root 3 tan theta. That gives us root 3 tan squared theta. Then we have negative tan theta times 1. That's negative tan theta. Tan theta. Then we have root 3 times negative root 3 tan theta. That is negative 3 tan theta. And then we've got root 3 times 1. That is positive root 3. Now we have to simplify like terms. We've got root 3 tan squared theta. Then we have tan theta plus 3 tan theta. That is 4 tan theta plus root 3 plus root 3. This is equal to, so 2 times 1, that's 2. Then 2 times negative 3 tan squared theta, that's negative 6 tan squared theta plus root 3 tan squared theta, root 3 tan squared theta minus tan theta minus 3 tan theta, so that's minus 4 tan theta plus root 3. Okay, let's simplify again. We have root 3 tan squared theta plus 4 tan theta plus root 3 is equal to, we have 2 minus 6 tan squared theta plus root 3 tan squared theta. So that's plus minus 6 plus root 3. And this is tan squared theta minus 4 tan theta plus root 3. Let's move all the terms to the left hand side. So we end up with root 3 tan squared theta minus negative 6 plus root 3 tan squared, close this bracket, tan squared theta, and then we have plus 4 tan theta. Then this minus 4 tan theta becomes a positive 4 tan theta. And then we've got root 3. And then we've got minus this root 3. Minus root 3. And then we have minus 2. Minus 2. And this is equal to 0. So for the tan squared theta, we've got root 3 minus 6 plus root 3. So that's root 3. If we get into the bracket, that would be plus 6 minus root 3. We've multiplied through by this negative sign, and this is tan squared theta. So let's probably simplify that first. The root 3's will cancel out and you end up with 6 tan squared theta. So that's 6 tan squared theta. And then we've got 4 tan theta plus 4 tan theta, that's 8 tan theta. 8 tan theta. And then root 3 minus root 3 will cancel out, so we end up with negative 2. And this is all equal to 0. Let's divide through by 2 to simplify our quadratic. It becomes 3 tan squared theta plus 4 tan theta minus 1 is equal to 0. And now we have our quadratic in terms of tan theta. Okay, so let's use the quadratic formula to solve our quadratic equation. Tan theta is equal to minus 4 plus or minus the square root of, that's b squared, which is 4 squared, minus 4a, which is 3, and c, which is negative 1. And then over 2 times a, that's 2 times 3. Let's punch this into the calculator. This is minus 4 plus the square root of 4 squared minus 4 times 3 times minus 1. And this is all over 2 times 3. And this gives us negative 2 plus or minus root 7 and this is all over 3. Let's write this as two separate equations. So that's tan theta is equal to negative 2 plus root 7 over 3. And then we have tan theta is equal to negative 2 negative root 7 over 3. Now let's solve both equations. We'll start with the first one. Theta is equal to arctan of negative 2 plus root 7 over 3. And theta is equal to, we are in degrees, so make sure your calculator is in degrees. That is arctan of negative 2 plus root 7 over 3. And that gives us 12.14759447. Now our interval is that theta should be between 0 degrees and 180 degrees. So this will be our only solution from this equation over here. Now let's solve that equation. That's theta is equal to arctan of negative 2 negative root 7 over 3. Theta is equal to, if we punch that into the calculator, that is arctan of negative 2 negative root 7 over 3. And that gives us negative 57.14759447. Now this is outside of our given interval. So we'll use PV plus 180n to get the solution that's within the interval. Substitute n with 1. You get, this is the principal value over here. So that would be PV plus 180 times 1, and you get, so PV plus 180 times 1, that gives us 122.8524055. And this solution is actually within our given interval. So we can conclude that therefore theta is equal to 12.1 degrees, and then we've got theta is equal to 122.9 degrees from here, and this would be our final answer. Part A. Show that cos 3x over sine x plus sine 3x over cos x is equal to 2 cot 2x. Okay, so we are given cos 3x over sine x plus sine 3x over cos x, and this is equal to 2 cot 2x. So we're going to work with the left hand side, and remember that cot 2x can be written as in this case that's cos 2x over sine 2x. So we're going to work from the left hand side, trying to get to the stage over here. So let's start by combining our two fractions. So our common denominator will be sine x cos x, and then our numerator, that is, we've got cos 3x here, it's multiplying cos x plus sine 3x sine x. And now we're going to rewrite cos 3x as cos 2x plus x, which will allow us to use the formula for the compound angle formula for cos, and we'll do the same for sine. So that's sine 2x plus x times sine x, and this is all over sine x cos x. Okay, and now let's expand using our compound angle formula. So we get, let's put a big bracket over here, that is cos 2x cos x minus sine 2x sine x, and this is being multiplied by cos x, and then here we get plus, let's put a big bracket again, that's sine 2x sine 2x cos x plus cos 2x sine x, and this is being multiplied by sine x, and this is all over sine x cos x. So what we have is cos 2x cos x multiplied by cos x, so that becomes cos 2x cos squared x, and then we have minus sine 2x sine x multiplied by cos x, so that's minus sine 2x sine x cos x, and then we have sine 2x cos x multiplied by sine x, so that would be plus sine 2x sine x cos x, and then we've got cos 2x sine x multiplied by sine x, so that's plus cos 2x sine squared x, and this is all over sine x cos x. Okay, so in our numerator, you notice that these two over here will cancel out. So you end up with cos 2x cos squared x plus cos 2x sine squared x, and this is over sine x cos x. So to simplify, we're going to use the identity cos squared x is identical to 1 minus sine squared x. So here where there's a cos squared x, we're going to substitute it with 1 minus sine squared x. So that becomes cos 2x times 1 minus sine squared x plus cos 2x sine squared x, and this is all over sine x cos x. So let's expand. That's cos 2x minus cos 2x sine squared x plus cos 2x sine squared x, and this is all over sine x cos x. In our numerator, you notice that these two terms will cancel out, and so we end up with cos 2x over sine x cos x. Remember, we said we are trying to get to 2 cos 2x over sine 2x. So we're still missing this 2, and we still need a sine 2x. Now we're going to play around with our denominator. If we go to the double angle formula for sine, so that's sine 2x, that is equal to 2 sine x cos x. Notice how this is very similar to the denominator that we have. If we come to our double angle formula, let's make our denominator, which is sine x cos x, the subject of the formula. That becomes sine x cos x is equal to, we have to divide both sides by 2 or multiply by half sine 2x. And let's come here and substitute our denominator with half sine 2x. We end up with cos 2x divided by sine 2x over 2. And if we resolve our fraction, we end up with 2 cos 2x over sine 2x, which is exactly what we were trying to get to, right? That's 2 cos 2x over sine 2x here, and then that should simplify to give us that. So let's just show the working of how that then goes to cot 2x. So this then becomes 2 over sine 2x over cos 2x, which is 2 over tan 2x, and that gives us 2 cot 2x, and we have proved our identity. and solve the equation cos 3x over sine x plus sine 3x over cos x is equal to 4. So we can simply replace this bit here with 2 cot 2x. So we want 2 cot 2x is equal to 4. Okay, so we have 2 cot 2x is equal to 4. Let's write cot 2x in terms of tan. So that's 2 over tan 2x is equal to 4. So you end up with tan 2x is equal to 2 over 4, which is half. So 2x is equal to arctan of 1 over 2. 2x is equal to, let's punch this into a calculator, that is arctan of 1 over 2. And we are in radians, so make sure your calculator is in radians. So arctan of half, let me change my calculator to radians. Arctan of half will give us 0.463647609. So this value that we have over here, this would be our principal value. So let's use that to get the other solutions that will be within the given interval. So we're going to use PV plus 1, or we're in radians now, so that's plus pi n. So at n is equal to 1, we have our principal value plus pi times 1. So if we punch this into a calculator, that's our principal value. That's the 0.463647609 plus pi, and that gives us 3.605240263. So remember that we have taken this from 2x, so 2x is equal to 3.605240263. So now let's simplify both solutions here. We'll simplify the principal value first. So if we simplify our principal value, that's dividing it by 2, you get x. X is equal to 0.232, correct to 3 significant figures. And then if we simplify here, that's dividing by 2. Divide by 2, you get x is equal to 1.80, correct to 3 significant figures. And the question states that our interval is between 0 and pi. So we can conclude that therefore x is 0.232 and 1.80, and that's our final answer. Express root 2 cos x minus root 5 sin x in the form r cos x plus alpha, where r is greater than 0 and alpha is between 0 and 90 degrees. Give the exact value of r and the value of alpha correct to 3 decimal places. Okay, so we can find r by simply saying r is the square root of, that is, root 2 squared plus root 5 squared. Punch that into the calculator. This is the square root of root 2 squared plus root 5 squared, and that gives us root 7. And then to find alpha, we're going to say that tan alpha is equal to root 5 over root 2. So alpha must be equal to arctan of, we can also just write this with 1 square root sign as root 5 over 2. So that's what I'll do here. This is arctan of root 5 over 2. Alpha is equal to, let's punch that into the calculator, arctan root 5 over 2. And this gives us 57 point, they want it correct to 3 decimal places, so that's 688 degrees. And we can conclude that therefore root 2 cos x minus root, that should be root 5 sine x, is equal to root 7 cos x plus 57.688 degrees, and this would be our final answer. That's it for the trig video. You can now go on to work on the topical questions. See you in the next video. Welcome to the differentiation section of our BO3 crash course. Let's get into it. The curve with equation y equals e to the 2x times sine x plus 3 cos x has a stationary point in the interval x is between 0 and pi. Part A. Find the x coordinate of this point, giving your answer correct to 2 decimal places. So we want to find a stationary point, so we have to first find dy dx. So we are given that y is equal to e to the 2x times sine x plus 3 cos x. So dy dx is equal to, we're going to use the product rule here. So let's hold e to the 2x and let's differentiate what's in the bracket. If you differentiate sine x, you get cos x. If you differentiate 3 cos x, you get negative 3 sine x plus, now let's hold the bracket, that's sine x plus 3 cos x. If you differentiate e to the 2x, you get 2e to the 2x. So dy dx is equal to, let's start by factoring out our e to the 2x. So e to the 2x, so what we end up with is this bracket over here, cos x minus 3 sine x, 3 sine x plus 2 times this bracket over here, sine x plus 3 cos x. Let's close our big square brackets. So this gives us e to the 2x, and this is cos x minus 3 sine x. Let's expand our bracket. That's plus 2 sine x plus 6 cos x, which further simplifies to give us e to the 2x. We have cos x plus 6 cos x, so that's 7 cos x, minus 3 sine x plus 2 sine x, so that's minus sine x. And this would be dy dx. So since we want a stationary point, we're going to equate dy dx to 0. So this becomes e to the 2x times 7 cos x minus sine x is equal to 0. So we then say e to the 2x is equal to 0, and our bracket 7 cos x minus sine x is equal to 0. So if we take the natural logarithm of both sides here, we get 2x is equal to ln 0. We get x is equal to no solutions. So now let's move on to this equation over here. Let's divide through by cos x. So that will become 7 minus sine x over cos x, which is tan x, and this is equal to 0. So tan x is equal to 7. X is equal to arctan of 7. X is equal to, let's evaluate arctan of 7. We are in radians, so make sure your calculator is in radians. Arctan of 7, and that gives us 1.43, and this would be our final answer. They say they want it correct to 2 decimal places, so we'd conclude that therefore x is equal to 1.43. Part B. Determine whether the stationary point is a maximum or a minimum point. Okay, so we're not going to treat this like at AS level. At AS level, you just simply find the second derivative and then substitute your x value. But the functions that we're now dealing with are a lot more complicated, so it would take too much time to get the second derivative and then substitute x. So what we're going to do is that, let me draw these two curves over here. So this curve over here has a maximum point here, and this curve has a minimum point. So if we come and draw a tangent to the left of our stationary point, you can tell that this tangent over here has a positive gradient for a maximum point, and for a minimum point to the left, we've got a negative gradient. So we're going to pick any point that's to the left of our stationary point. So here we have 1.43, and we're going to substitute that into dy dx. So dy dx is e to the 2x times 7 cos x minus sin x. So let's substitute x with 1. So that becomes e to the 2 times 1. And then that's 7 cos 1 minus sin 1. Let's punch that into our calculator. That is e to the 2 times 7 cos 1 minus sin 1. And we get 21.7 and so on, right? So now you notice that we have a positive gradient to the left of our stationary point. So which of these two scenarios represents a positive gradient to the left of our stationary point? So it's this scenario where we have a maximum point. We can tell that the tangent here has a positive gradient. So we can conclude that therefore we have a maximum point. And this would be our final answer. The equation of a curve is y e to the 2x minus y squared e to the x is equal to 2. Show that dy dx is equal to 2y e to the x minus y squared over 2y minus e to the x. So this is an implicit function. So that becomes d dx of y e to the 2x minus y squared e to the x is equal to 2. And so let's start with this first term over here. We'll use the product rule, so that's, let's hold y and let's differentiate e to the 2x. You get 2e to the 2x. And then now let's hold e to the 2x and differentiate y. You get dy dx. Then let's move on to our second term over there. That is, let's hold the negative y squared first and differentiate e to the x. So you get e to the x. And then now let's hold the e to the x and differentiate the negative y squared. So you get negative 2y dy dx. And if we differentiate 2, we get 0. Let's simplify. So we've got 2y e to the 2x plus e to the 2x dy dx minus y squared e to the x minus 2y e to the x dy dx is equal to 0. Okay, now let's put the terms containing dy dx on one side. So we're moving them to the right hand side. That will be 2y e to the x dy dx. That's this term over here. We've moved it to the right hand side. And then if we move this term to the right hand side, that becomes minus e to the 2x dy dx. And this is all equal to, we have 2y e to the 2x, 2y e to the 2x minus y squared e to the x. Let's factor out dy dx on the left hand side. So dy dx, that becomes 2y e to the x minus e to the 2x. And this is all equal to 2y e to the 2x minus y squared e to the x. This should be x. And so dy dx is equal to 2y e to the 2x minus y squared e to the x. And this is over 2y e to the x minus e to the 2x. And what are we trying to show? We're trying to show that dy dx is equal to 2y e to the x minus y squared over 2y minus e to the x. Okay, so that means we have to factor out e to the x in both the numerator and denominator. So if we factor out e to the x here, you get 2y e to the x minus y squared, and this is over e to the x, that's 2y minus e to the x, and so these will cancel out, and you end up with dy dx is equal to 2y e to the x minus y squared over 2y minus e to the x. And this is what they want us to prove, so that would be our final answer. Now let's move on to part B. Find the exact coordinates of the point on the curve where the tangent is parallel to the y-axis. So the y-axis looks like this, right? So if you have a tangent that is parallel to the y-axis, then we are saying that we do not have any change in the x direction. So in other words, dx is equal to 0. So from dy dx, this dx part is the one that is equal to 0. So we can come to this dx and we can equate the dx part to 0. So 2y minus e to the x is equal to 0. And then we can also use the equation of the curve, since we want the point on the curve where the tangent is parallel to the y-axis. So we're going to use y e to the 2x minus y squared e to the x is equal to 2. We're going to solve these two equations simultaneously. So let's start by making y the subject of the formula in this equation. So 2y is equal to e to the x, and you get y is equal to e to the x over 2. Let's substitute that into our equation of the curve. So that becomes e to the x over 2 times e to the 2x minus e to the x over 2, and this is squared. Then we've got e to the x, and this is equal to 2. Okay. So this becomes e to the 3x over 2, and then here we have minus. Let's square everything. You get e to the 2x over 2 squared, which is 4, times e to the x, and this is equal to 2. So this becomes e to the 3x over 2 minus, that becomes e to the 3x over 4, and this is equal to 2. Now let's simplify the coefficient of e to the 3x. So that's half minus a quarter, 1 over 2 minus 1 over 4. And so we have a quarter e to the 3x, and this is equal to 2. Multiply both sides by 4. You get e to the 3x is equal to 8. And let's apply the ln function on both sides. You get 3x is equal to ln 8. And so x is equal to 1/3 ln 8. Did they specify the degree of accuracy? They want the exact coordinates. So x is 1/3 ln 8. And now we have to evaluate y. In fact, let's actually simplify this x further. We can write this as x is equal to ln 8 to the power 1/3, or in other words, the third root of 8. And we know that the third root of 8 is 2, so this is ln 2. Now let's evaluate y. So y is equal to e to the x. Y is equal to e to the x is ln 2, and this is all over 2. So that will cancel out, and you get 2 over 2. So y is equal to 1, and we can conclude that our coordinates are ln 2 and 1, and this would be our final answer. The parametric equations of a curve are x is equal to cos theta over 2 minus sine theta, and y is equal to theta plus 2 cos theta. Show that dy dx is equal to 2 minus sine theta squared. Okay, so let's start by writing down our parametric equations. We have x is equal to cos theta over 2 minus sine theta. And then we have y is equal to theta plus 2 cos theta. Let's find dx d theta, which is simply differentiating this. We're going to use the quotient rule here. Okay, so let's hold our denominator and differentiate our numerator. If you differentiate cos theta, you get negative sine theta times negative sine theta minus, now let's hold our numerator and differentiate 2 minus sine theta. So if we differentiate 2, that's a constant, we get 0. And then if you differentiate minus sine theta, you get minus cos theta. So this is minus cos theta. And this is all over our denominator squared. So that's 2 minus sine theta squared. Okay, so let's simplify that. Dx d theta is equal to, let's expand our numerator. You've got negative 2 sine theta, negative 2 sine theta plus sine squared theta. Then we've got minus cos theta, that gives us a positive cos squared theta. And this is all over 2 minus sine theta squared. And then you notice that this section over here, is equal to 1. Using the identity, sine squared theta plus cos squared theta is equal to 1. So dx d theta can be written as 1 minus 2 sine theta over 2 minus sine theta squared. Okay, that is our simplest. We'll leave dx d theta like that for now. Now let's find dy d theta. So if you differentiate theta, you get 1. And then if you differentiate 2 cos theta, you get negative 2 sine theta. And now let's create a chain rule for dy dx. Dy dx, let me scroll up so that you can see clearly. Dy dx is equal to dy d theta multiplied by d theta dx. Okay, so dy d theta is 1 minus 2 sine theta. So dy dx is equal to dy d theta, which is 1 minus 2 sine theta. And this is being multiplied by d theta dx. We want d theta dx, but here we have dx d theta. So I'm just going to simply flip our fraction here to get d theta dx. So that gives us 2 minus sine theta squared over 1 minus 2 sine theta. And so this will cancel with that, and you end up with dy dx is equal to 2 minus sine theta squared. And this is our final answer. We have proved that dy dx is equal to 2 minus sine theta squared. That's it for the differentiation video. You can now go into the topical questions and see you in the next video. Welcome to the integration section of our PO3 crash course. Let's get straight into it. Let f of x equal cos x over 1 plus sine x. Find the integral from 1 over 6 pi to 1 over 2 pi of f of x with respect to x. Give your answer in a simplified exact form. Okay, so we are integrating, that's cos x over 1 plus sine x, and this is with respect to x. So for this, we're going to use what we call the method of recognition, which states that the integral of f prime of x over f of x with respect to x is equal to ln f of x. So if you differentiate your denominator here, that's 1 plus sine x. If you differentiate 1, you get 0. If you differentiate sine x, you get cos x. So you notice that our numerator is the differential of our denominator. So we can use this method, which is called the method of recognition. So that means our integral will now become ln f of x. So f of x is 1 plus sine x. So we can go on to say that ln 1 plus sine x is our integral. And then our limits are from 1 over 6 pi to 1 over 2 pi. Let's go on to substitute in our limits. So we've got ln 1 plus sine, let's start with our upper limit, that's 1 over 2 pi, minus our lower limit, ln 1 plus sine 1 over 6 pi. Let's close our bracket, and now let's punch this into a calculator. This would become ln 1 plus sine half pi. Make sure you're in radians. Sine 1 over 2 pi gives us 1, so that's ln 1 plus 1 minus ln 1 plus, let's do sine 1 over 6 pi. That gives us a half, so you end up with ln 2 minus ln 3 over 2. Now we can use laws of logarithms to combine these two logarithms to become 1, so that's ln 2 divided by 3 over 2, which would simplify to give us ln 4 over 3, and this would be our final answer. Find the exact value of the integral from 0 to a quarter pi of x sec squared x with respect to x. Okay, so you can tell that we have two functions multiplying each other, so we're going to use integration by parts. Okay, so let u equal x, and then dv dx will be our sec squared x. So du dx, if you differentiate x, you get 1, and if you integrate sec squared x, we get tan x. And now let's go to the formula for integration by parts. So that's the integral of x sec squared x with respect to x, and this is equal to uv, which is x tan x, minus the integral of v du dx, which in this case is 1 times tan x, so just the integral of tan x with respect to x. So we need to find the integral of tan x. Let's do that on the side. So we want to integrate tan x with respect to x. We can write tan x as sine x over cos x with respect to x. Now notice that if you differentiate the denominator, that's cos x, you get negative sine x, which is very similar to our numerator. So let's write it like that. Let's write our numerator as sine x. So like this, that's cos x with respect to x. So now our numerator is the differential of the denominator. But the problem is the numerator, our original numerator, is not negative sine x. So we're going to multiply outside the integral sign by a negative sign so that this is equal to what we have originally. And now we can use the method of recognition that we used in the first question, and we can say that this should be equal to negative ln f of x being the denominator, so ln cos x. So that means the integral of tan x is equal to negative ln cos x. So we can come back to our formula for integration by parts and say that this is equal to x tan x minus ln cos x. So that will be plus ln cos x. And that's our integral for x sec squared x with respect to x. Now let's put our limits. So this is x tan x plus ln cos x, and this is going from 0 to 1 over 4 pi. Let's substitute in our limits. We'll start with our upper limit. So that's a quarter pi, 1 over 4 pi, times tan 1 over 4 pi plus ln cos 1 over 4 pi. Okay, minus our lower limit. So this will be the first term, there will be a 0, so that will cancel out. So we'll go straight to ln cos of 0. And now let's simplify. So we have a quarter pi. Let's evaluate tan a quarter pi with our calculator. Tan 1 over 4 pi, that gives us 1, so this is times 1, plus ln cos 1 over 4 pi, cos 1 over 4 pi, that gives us root 2 over 2. So we have ln root 2 over 2 minus ln cos 0. Cos 0 is equal to 1, and we know that ln 1 is equal to 0. So this will still just simply be 0. And now let's simplify this. Our final answer would be 1 over 4 pi plus ln root 2 over 2. By using the substitution u is equal to root x, find the exact value of the integral from 3 to infinity of 1 over x plus 1 times root x with respect to x. Okay, so we've got the integral from 3 to infinity of 1 over x plus 1 times root x with respect to x, and we're given the substitution u equals root x. Let's start by substituting our limits. So we've got at x is equal to 3 and at x is equal to infinity. So at x is equal to 3, you get u is equal to root 3. Then at x is equal to infinity, you get u is equal to root infinity. Okay, so this may be a little difficult to take, but root infinity is equal to infinity. Some infinities are bigger than others. The idea is basically that if you take the square root of a very large number, which is infinity, you still remain with a very large number, which is still infinity. So in this case, u is going to be infinity. So our limits are now, our lower limit is root 3, our upper limit is still infinity, and we have 1 over x plus 1 root x dx, and now we want to substitute dx. So we're going to do that by simply differentiating our substitution. So I'll write root x as x to the half so that we can differentiate. So du dx is equal to, we bring down the power, that becomes half x, subtract 1 from the power, that becomes minus half, and we can write this as du dx is equal to 1 over 2x to the half, which is the same as root x. And now we want to make dx the subject of the formula, so we can do that by cross multiplying, and you get dx is equal to 2 root x du. And now let's substitute dx with 2 root x du. So what we have is, our lower limit is root 3 and we have infinity, and this is 1 over x plus 1 root x, and we're substituting dx with 2 root x du. Now notice that this root x and that root x will cancel out, and so this simplifies to our integral from root 3 to infinity, and that is 1 over x plus 1, or multiplying by 2. So let's make our numerator 2. So this is 2, and this is with respect to u. So the last thing that we have to substitute is this x over here. So our substitution is u is equal to root x. We can make x the subject of the formula by squaring both sides to get x is equal to u squared. And so if we come back to our integrand, we've got the integral of root 3 to infinity 2u squared plus 1 with respect to u. Now everything is in terms of u and we can go on to integrate. But before we integrate, I'm just going to take the 2 behind our integral sign. So that is 2, the integral of root 3 infinity of, oh, that's now 1 over u squared plus 1 with respect to u. So now if we integrate this 1 over u squared plus 1, we get arctan of u. And this is from root 3 to infinity. And now let's substitute in our limits. So we've got arctan of, our upper limit is infinity, minus our lower limit arctan of root 3. And this is, let's close our bracket. Okay, so arctan of infinity, if we are to draw, let's draw the graph of y equals tan x so that we see what's going on here. So we have our, this will be our x-axis, and then rather this is the y-axis and this is the x-axis. So we'd have something like this, and then you'd have an asymptote over here, right? So if we are to actually extend this graph, you know that this line over here, our function, will never touch the asymptote, but it will continue to increase and it will approach infinity. So you can see that. So we know that this asymptote here is at half pi or 90 degrees if you want to put it in degrees. So we know that as y continues to increase towards infinity, it's approaching half pi. So we can just approximate arctan of infinity to be equal to half pi. So this becomes half pi. And then we're subtracting arctan of root 3, arctan of root 3. That gives us 1 over 3 pi. So minus 1 over 3 pi. So let's punch that into the calculator. We have 2 times 1 over 2 minus 1 over 3 pi. So this gives us 1 over 3 pi. And this would be our final answer. Welcome to the numerical solutions video. Let's get straight into it. Part A. By sketching a suitable pair of graphs, show that the equation sec x is equal to 2 minus half x has exactly one root in the interval x is between 0 and half pi. Okay, so that would mean we have to sketch the graph of y equals sec x, and then the graph of y equals 2 minus half x. This is between 0 and half pi, so let's draw our Cartesian plane. So this would be our y-axis, and then we've got our x-axis here. This is the x, and we say half pi is somewhere around here. Okay, and then we have the graph of y equals sec x. So it starts at 1. It would look something like this. There's an asymptote at half pi for that graph. So this would be y equals sec x. Then in red, we'll do the graph of our line. So we need 2 points since this is a straight line. So when x is 0, we get y is 2. And then we need another point. So when x is equal to 1, y is 1.5. And now let's use these 2 points. So 0, 2 would be somewhere here. And then we have 1, 1.5. So half pi, if we punch that into a calculator, half pi is approximately 1.57. And we're looking for 1. So we're saying 1 would probably be somewhere here. So this would be 1. And then we're saying about 1.5 in the y-axis. So about 1.5 would be somewhere over here. and we're drawing a line going through these 2 points like that. It should look something like this. This would be the line of y equals 2 minus half x. And we can tell that we have exactly one root in our interval, which is this point of intersection. And this would be our final answer for part A. Okay, let's move on to part B. Part B states that verify by calculation that this root lies between 0.8 and 0.1. Okay, let's just get rid of this diagram first so that everything is clear. So we are required to find by calculation or verify by calculation that this root lies between 0.8 and 0.1. To do that, we're going to use the equation they gave us in part A, which is sec x is equal to 2 minus half x. We're going to put everything on one side and we're going to equate this to f of x. So f of x is to sec x minus 2 plus half x. And now we're going to evaluate f of 0.8 and f of 1. So f of 0.8 is equal to sec 0.8 minus 2 plus half times 0.8. And f of 0.8 gives us, if you punch that into the calculator, make sure you're in radians. And remember that sec x is the same as 1 over cos x. So this is 1 over cos 0.8 minus 2 plus 1 over 2 times 0.8. And this gives us negative 0.165, correct to 3 significant figures. And if we evaluate f of 1, that is sec 1 minus 2 plus half times 1. So f of 1 is equal to, let's punch that into the calculator, that is 1 over cos 1 minus 2 plus half times 1, and this gives us 0.351 to 3 significant figures. And notice how this is positive, but our first answer here is negative. So we can conclude that, therefore, since there is a change in sign in sign, a root lies between 0.8 and 1. And this would be our final answer for part B. Part C. Use the iterative formula xn plus 1 is equal to arc cos of 2 over 4 minus x to the n to determine the root correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay, let's get rid of part B. Okay, so our iterative formula is xn plus 1 is equal to arc cos of 2 over 4 minus xn. We know that our root lies between 0.8 and 0.1. So we're going to say let x0 equal 1. And then from there onwards, we're going to use our iterative formula. So that is arc cos of 2 over 4 minus, this would be x0, so that's 1. 4 minus 1. Let's punch this into our calculator. Arc cos of 2 over 4 minus 1, and this gives us 0.8411. They want the result of each iteration to 4 decimal places. Let's go on to x2, the second iteration. That's arc cos of 2 over 4 minus. So instead of using the value of the previous iteration here, you're just going to use the answer function on your calculator. So simply replace the 1 with ans and press equals. You get 0.8852. Correct 2 4 decimal places, and then x3. Don't change anything on your calculator, just simply press equals, and you get the result of the next iteration, which is 0.8736. And we go on to the next iteration, that is 0.8767, and we go on to the next iteration, x5, that is 0.8758, and if we round these two iterations off to 2 decimal places, they give us 0.88, and we can conclude that therefore the root is 0.88, and this would be our final answer. The equation cot half x is equal to 3x has one real root in the interval x is between 0 and pi, denoted by alpha. Show by calculation that it lies between 0.5 and 1. Okay, so we are given the equation cot half x is equal to 3x. Now let's put everything to one side and we will call this function f of x. So f of x is equal to cot half x. We'll move the 3x to the left hand side, so it becomes minus 3x. Now we need to show that alpha lies between 0.5 and 1. So we're going to evaluate our function f of x when x is 0.5. So cot can also be written as 1 over tan. So that's tan half x. So that's half times 0.5 minus 3 times 0.5. So f of 0.5 gives us, this is 1 over tan half times half minus 3 times half, which gives us 2.416. And then let's evaluate f of 1. F of 1 is equal to 1 over tan 1, or rather half, times 1 minus 3 times 1. Let's punch this into a calculator. So that's 1 over tan half times 1 minus 3 times 1. And this gives us f of 1 is equal to negative 1.1695, and so on. So you can tell that there is a change of sign because this is positive and this is negative. So we can conclude that since there is a change in sign, a root lies between 0.5 and 1. And that will be our final answer for part A. Part B, show that if a sequence of positive values by the iterative formula xn plus 1 is equal to 1/3 times xn plus 4 arctan of 1/3 xn converges, then it converges to alpha. Okay, so this is just a fancy way of saying that show that this equation simplifies to give this equation. So if we remove all the n's and n's plus 1, that is x is equal to 1 over 3, then we have a bracket, that's xn plus 4 arctan of 1 over 3 xn, or let's remove the n. So that's just x, and then let's close our brackets. And we have to show that this equation simplifies the equation we were given in this term of the question. So let's start by multiplying both sides by 3. So that becomes 3x. That n should not be there. Let's remove that. So this becomes x plus 4 arctan of 1 over 3 x. Then let's move this x to the left hand side so that it becomes 3x minus x equal to 4 arctan of 1 over 3x, and this becomes 2x is equal to 4 arctan of 1 over 3x. Let's divide both sides by 4, so you get half x is equal to arctan of 1 over 3x. Let's apply tan to both sides, so this becomes tan of x is equal to 1 over 3x. And then if we move this 3x to the left hand side, this becomes 3x is equal to 1 over tan of a half x. And this simplifies to give us 3x is equal to 1 over tan half x is the same as cot half x. What are we trying to prove? We are trying to prove that cot half x is equal to 3x. So let's just write in that order. Cot half x is equal to 3x. And we have proved that if a sequence of positive values by the iterative formula converges, then it converges to alpha. Now part C, use this iterative formula to calculate alpha correct to 2 places. Okay, let's just clean this up first. So our iterative formula is given here. Xn plus 1 is equal to 1/3 xn blah blah blah. And we know that our root alpha is between 0.5 and 1. So we'll say let x0 equal to 1. So let's evaluate x1. x1 will then be 1 over 3 x0, which is 1, plus 4 arctan of 1 over 3 times x0. x0 is 1. And we need to punch that into a calculator. And we are in radians. This is 1 over 3 times 1 plus 4 arctan of 1 over 3 times 1, and then let's close our brackets. We get 0.7623, and this is correct to 4 decimal places. Now we need to evaluate x2. So x2 is equal to 1/3. Now everywhere where we put x0 in x1, we're going to replace that with ans. So that's here and here. Use the answer function on your calculator. So that's 4 arctan of 1 over 3 times answer. This is equal to, so in your calculator just simply replace the x0 with ans and don't change anything else, and press equals. You get 0.8037, and x3 is equal to, don't change anything on your calculator, simply press equals, and you get 0.7921, and then x4, press equals, 0.7951, and then we'll go on to x5. x5, press equals, you get 0.7943, and then x6, press equals, you get 0.7945. And now we have reached our root alpha, so that's 0.79, correct to 2 decimal places, and that's 0.79. So we can conclude that therefore alpha is 0.79, correct to 2 decimal places, and that is our final answer. So that's it for the numerical solutions video. You can now go into the topical questions and see you in our next video. Welcome to the vectors section of our PO3 crash course. Let's dive right in. Relative to the origin, the points A, B, and C have position vectors given by OA is 2, 1, 3, OB is 4, 3, 2, and OC is 3, negative 2, negative 4. The quadrilateral ABCD is a parallelogram. Part A, find the position vector of D. Okay, so we are given that we have a parallelogram ABCD. So it would look something like this. So we've got, this would be A to B, and then we'd have B to C, C to D, and then finally this would be D back to A. Okay, so this is A, B, C, and D, and this would be parallel to that, and this AD would be parallel to BC. So we are required to find the position vector of D. We can use the idea that the displacement vector of AB would be the same as the displacement vector of DC. So let's write that down. That is AB is equal to DC. And we know that we can find AB by saying OB minus OA. And we can find DC by saying OC minus OD. So since we're looking for OD, let's make it the subject of the formula. So that becomes OD is equal to, this would be OC plus OA minus OB. And now we can simply substitute in the values and evaluate OD. So we know that OC has been given as 3, negative 2, negative 4. Okay, so that's 3, negative 2, negative 4 plus OA, which has been given as 2, 1, 3, 2, 1, 3 minus OB, which is 4, 3, 2, 4, 3, 2. So now let's evaluate OD. So we've got 3 plus 2, that's 5, minus 4, that's 1, minus 2 plus 1, that's minus 1, minus 3, that's minus 4, minus 4 plus 3, that's minus 1, minus 2, that's minus 3. So we can conclude that therefore the position vector of D is 1, negative 4, negative 3, and that would be our final answer. Let's move on to part B. The angle between BA and BC is theta. Find the exact value of cos theta. Okay, let's just clear out our working out for part. So in part B, we want to find cos theta. So that's the angle between two vectors. Cos theta is equal to, we were told the angle between BA and BC. So our formula would be the dot product of BA and BC over the product of their moduli. Modulus of BA and modulus of BC. Okay, so let's start by finding the actual displacement vectors of BA and BC. So BA would be equal to OA minus OB. So BA would therefore be equal to, what's our column vector for OA? That is 2, 1, 3. So we've got 2, 1, 3 minus our column vector for OB. That is 4, 3, 2. 4, 3, 2. And BA would be equal to, so that's 2 minus 4, that's minus 2. 1 minus 3, that's minus 2. 3 minus 2, that's 1. Okay, so this is our displacement vector for BA. Now let's find the displacement vector for BC. So BC would be equal to OC minus OB. So BC would be equal to our position vector for C, that is 3, -2, -4. 3, -2, -4 minus our position vector for B, that's 4, 3, 2. 4, 3, 2. And if we subtract, we get that BC is equal to, that's 3, 3 minus 4, that gives us -1, -2, -3, that's -5, -4, -2, that's -6. Okay, so now that we have both the displacement vectors of BA and BC, we can go on to find their dot product. So we want BA dot BC. So we say BA is over here, -2, -2, 1 dot BC, which is -1, -5, -6. So that would be -2 times -1, that gives us 2, plus -2 times -5, which gives us 10. And then we've got 1 times -6, which gives us -6. So this becomes 2 plus 10, which is 12, minus 6, which is 6. So that means our dot product is 6. Now we need to evaluate both the moduli of BA and BC. So we'll start with the modulus of BA, that is equal to the square root of, that's -2 squared plus -2 squared plus 1 squared. So the modulus of BA is equal to, if we punch this into a calculator, that's the square root of -2 squared plus -2 squared plus 1 squared, and that gives us 3. This is the modulus of BA, and for the modulus of BC, that is the square root of -1 squared plus -5 squared plus -6 squared. Now let's punch that into our calculator. That is the square root of -1 squared plus -5 squared plus -6 squared. And this gives us root 62. Okay, so now that we have both the dot product and the moduli, we can go back to our formula for angle between two lines and substitute. So this would become cos theta is equal to the dot product, which we said is 6, over their moduli. So we've got 3 times root 62. 3 root 62. So we can cancel out, and that becomes cos theta is equal to 2 over root 62. So since they said they want us to find the exact value of cos theta, we can leave our answer here and say that therefore cos theta is equal to 2 over root 62. Part C, hence find the value of A, B, C, D, giving you answers in the form P root Q, where P and Q are integers. Okay, so the angle that was defined as theta in part B is the angle between BA and BC. So on our diagram, let's mark that angle in red. So this over here is the angle between BA, and BC. And we are told that this is angle theta. Okay, and so we can use this angle together with the idea of splitting our parallelogram into two triangles to help us find our area of ABCD. Okay, so we can find the area of the triangle by saying half AB times BC sine theta. Okay, so we evaluated AB. AB is the same as BA in terms of length, and we evaluated that in part B. The modulus of BA would be the same as AB, and that is 3. So you can come and say that this is half times 3 times BC. BC we evaluated to be root 62, root 62. This is root 62 times sine theta. Okay, so for theta, we could just use the answer that we got in part B and say theta is equal to arc cos of 2 over root 62, but then we wouldn't end up with an exact value. Notice how they say they want their answer in the form P root Q. So what we're going to do is that we know that from part B, we say cos theta is equal to 2 over root 62. Using our understanding of SOHCAHTOA, we can draw a right angled triangle using what we deduced in part B. Okay, so there's a right angle and let's call this angle theta. So we know that cos theta is equal to adjacent over the hypotenuse. So our adjacent here would be 2 and our hypotenuse would be root 62. So we don't know what the opposite is. We can use Pythagoras to evaluate our opposite side. So our opposite side would be equal to the square root of, that's root 62 squared minus 2 squared. Let's punch that into the calculator to evaluate the length of our opposite. So that's the square root of root 62 squared minus 2 squared, and that gives us root 58. Root 58. Okay, so that would mean that this side over here on our triangle is root 58. Now we can get the exact value of sine theta, and this will allow us to express our final answer in the form P root Q. Using our understanding of SOHCAHTOA, we know that sine theta is equal to opposite over the hypotenuse. So our opposite is root 58 and our hypotenuse is root 62. So what this means is that sine theta is equal to our opposite, which is root 58 over our hypotenuse, which is root 62. We can simplify this further by writing this as root 58 over 62. So sine theta is equal to root 58 over 62. Now we can come back to our expression over here and substitute sine theta with our exact value. So this would then become 1 over 2 times 3 times root 62 times root 58 over 62. And now let's punch this into a calculator and simplify. So that is 1 over 2 times 3 times root 62 times root 58 over 62. And this gives us 3 over 2 root 58. Okay. But remember that what we have only found, this only represents the area of this triangle over here. But we have 2 of these triangles, so that means we have to multiply by 2. So that's 3 over 2 root 58 multiplied by 2. So that 2 over there will cancel out, and we end up with our area of our parallelogram being 3 root 58, and that would be our final answer. Number 6. The points A and B have position vectors 2i plus j plus k and I minus 2j plus 2k respectively. The line L has vector equation r is equal to I plus 2j minus 3k plus mu times I minus 3j minus 2k. Part A. Find a vector equation for the line through A and B. Okay, so our vector equation is written in the form r equals a plus, in this case let's use lambda b. So a represents a point on the line and then b represents the direction vector on the line. So first we need to find this direction vector, and since this is a line through A and B, our direction vector will be a b. And to find it, we'll use the expression OB minus OA. Okay, so AB is equal to OB is I minus 2j plus 2k, I minus 2j plus 2k minus OA, which is 2i plus j plus k, 2i plus j plus k. AB is equal to I minus 2j plus 2k. Let's expand this bracket over here. So that's minus 2i minus j minus k. And now let's simplify. AB is equal to I minus 2i. That's minus 3i. Then we've got minus 2j minus j. That's minus 3j. And then we've got 2k minus k. That's plus k. And this would be the direction vector AB. Okay, so now we can write our vector equation. We say that R is equal to A represents a point that lies on the line. So for that, we're going to use the position vector of A over here. So that will be R is equal to 2i plus j plus k plus lambda. And we said B represents the direction vector of the line, and our direction vector is negative 3i, negative 3j plus k. So this would be the vector equation for the line through A and B. Part B. Find the acute angle between the directions of AB and L, giving your answers in degrees. Okay? So the formula for angle between two lines is cos theta is equal to, in this case, we're dealing with the direction of AB and L. So first we'd have to find their dot product, so AB dot L, and then their moduli, AB modulus of L. Okay, so let's start by finding their dot product. I'm going to write them as column vectors so that it's easier to see. So that's negative 3, negative 3, 1, negative 3, negative 3, 1, dot the direction of L, which is I minus 3j minus 2k. So that's 1 minus 3 minus 2. 1 minus 3 minus 2. Okay. So this would be negative 3 times 1, that gives us negative 3, and then negative 3 times negative 3, that is positive 9, 1 times negative 2, that is minus 2. So this becomes 9 minus 3, which is 6, minus 2, that's 4. Okay, so the dot product is equal to 4, and now we need to find the moduli of A, B, and L. Okay, so we'll start with the modulus of AB. That is equal to the square root of negative 3 squared plus negative 3 squared plus 1 squared. So the modulus of AB is equal to, this is the square root of negative 3 squared plus negative 3 squared plus 1 squared, and that gives us root 19. And then the modulus of the direction of L, this is equal to the square root of, this is the direction of L, so that is 1 squared plus negative 3 squared plus negative 2 squared. So the modulus of our direction here is, that's root 1 squared plus negative 3 squared plus negative 2 squared, and this gives us root 14. And now we just simply substitute into the formula for angle between two lines. So cos theta is equal to the dot product, which we said is 4, over root 19 times root 14. Root 19 times root 14. Okay, so theta is equal to arc cos. This is 4 over root 19 times root 14. And theta is equal to, let's punch this into our calculators, arc cos of 4 over root 19 times root 14, and this gives us 75.8 degrees, correct to 1 decimal place, and this would be our final answer. Part C, show that the line through A and B does not intersect the line L. Okay, so let me just clear up our solutions from A and B so that it's easier to visualize. Okay, so we have our equation for L, which has been given over here. We're going to write the vectors in there as column vectors so that it's easier to visualize. So we've got I plus 2j minus 3k, which is 1, 2, negative 3. And this is plus mu times that's 1 minus 3 minus 2. So this is the equation for L. And then we're going to do the same for the equation for the line through A and B. So that's R is equal to 2, 1, 1. And this is plus lambda. And we've got negative 3, negative 3, 1. Okay, so we're supposed to show that the line through A and B does not intersect the line L. So using these two equations, we can create 3 sets of equations. Since we're looking for a point of intersection, we're going to solve them simultaneously. So we'd have 1 plus mu times 1, 1 plus mu, and this should be equal to 2 plus lambda times negative 3, and that's 2 minus 3 lambda, and then we'd have 2 plus mu times negative 3, which is 2 minus 3 mu, which would be equal to 1 plus lambda times negative 3. So that's 1 minus 3 lambda. And we'd have negative 3 plus mu times negative 2. So that's negative 3, negative 2 mu. And this should be equal to 1 plus lambda times 1. So that's 1 plus lambda. Okay, so now we're going to use the first equation and we're going to make mu the subject of the formula. So that's mu is equal to 2 minus 1 minus 3 lambda. We've used this equation over here. So mu is equal to 1 minus 3 lambda. Now let's substitute it into the second equation. So that would be 2 minus 3. You said mu is 1 minus 3 lambda, so that's 1 minus 3 lambda, and this is equal to 1 minus 3 lambda. And so if we expand our bracket, that is 2 minus 3 plus 9 lambda is equal to 1 minus 3 lambda. Okay, so this is 2 minus 3, that's negative 1 plus 9 lambda is equal to 1 minus 3 lambda. Now let's make lambda the subject of the formula. So we've got 9 lambda plus 3 lambda is equal to 1 plus 1. That is, so this is 12 lambda is equal to 2. Divide both sides by 12. Lambda is equal to 1 over 6. So now that we have lambda, we can evaluate mu. Mu is equal to 1 minus 3 times lambda, which is 1 over 6. So mu is equal to, let's punch this into our calculator, 1 minus 3 times 1 over 6, and this gives us 1 over 2. So now that we have our values for lambda and mu, we're going to substitute them into the third equation. And if this third equation is satisfied by these two values of lambda and mu, then our equations intersect. But if it is not satisfied, then our equations do not intersect. So that's negative 3, negative 2 mu. Mu is 1 over 2. And this should be equal to 1 plus lambda. Lambda is 1 over 6. So let's simplify our left-hand side. That's negative 3, negative 2 times 1 over 2. And that gives us negative 4. And this should be equal to 1 plus 1 over 6, which gives us 7 over 6. So clearly we can tell that they are not equal. So we can conclude that not all three equations are satisfied, hence the lines do not intersect. The lines do not intersect, and this would be our final answer. So that's it for the vectors video. You can go on to the topical questions. See you in the next video. Welcome to the differential equations section of our Pure 3 crash course. Let's dive right in. The coordinates xy of a general point of a curve satisfy the differential equation x dy dx is equal to 1 minus 2x squared times y. For x is greater than 0, it is given that y equals 1 when x equals 1. Solve the differential equation obtaining an expression for y in terms of x. Okay, so we're given x dy dx, and this is equal to 1 minus 2x squared y. So the first step is to separate our variables. So that means everything containing x should be on one side and everything containing y should be on the other side. Okay, so if we move this y to the left hand side, it would become 1 over y, and then we'd keep the dy there, dy, and this should be equal to, we have this bracket over here, 1 minus 2x squared, and then we're going to move this x over here to the right hand side, so it's going to be dividing now, and then we are going to move this dx as well, so it will be multiplying. Okay, so that's 1 over y dy is equal to, now let's distribute the denominator here, so that becomes 1 over x minus 2x squared over x, and this is with respect to x. So if we simplify our right hand side, we have 1 over y dy is equal to 1 over x minus, here the x will cancel out with the squared, so you have minus 2x, and this is with respect to x. Now let's integrate both sides. So if you integrate 1 over y, you get ln y plus our constant of integration. Then if you integrate 1 over x, you get ln x minus, if you integrate 2x, that will be 2x squared over 2. So what we have is ln y plus c is equal to ln x minus the 2's cancel out, so x squared, and we are given that y equals 1 when x equals 1, so we can use those values to evaluate c. So this would be ln 1 plus c is equal to ln 1 minus 1 squared. Ln 1 is 0, so c is equal to negative 1 squared, which is negative 1. So this becomes ln y minus 1 is equal to ln x minus x squared. So they say they want an expression for y in terms of x, so that means we have to make y the subject of the formula. So that would become ln y is equal to ln x minus x squared plus 1. To get rid of this ln, we're going to use the exponential function, so apply it on both sides, and you get y is equal to e to the ln x minus x squared plus 1. Okay, and then using laws of indices, we can write this as y is equal to e to the ln x multiplied by e to the negative x squared plus 1. So y is equal to, the e and the ln x will cancel out, so you end up with x and then e to the negative x squared plus 1, and this would be our final answer. A certain curve is such that its gradient at a point xy is proportional to y over x root x. The curve passes through the points with coordinates 1, 1 and 4e. Part A. By setting up and solving a differential equation, find the equation of the curve expressing y in terms of x. Okay, so we are given that the gradient of a certain curve at a point xy, so that would be dy dx, is proportional to y over x root x, y over x root x. Okay, so we can write this as dy dx is equal to k, which is the constant of proportionality, y over x root x. So we can write x root x as x times x to the power half. And using laws of indices, we know that we simply add our powers since we have the same base, and this becomes x to the 3 over 2. So what we have over here is dy dx is equal to ky over x to the 3 over 2. Okay, so this would now be our differential equation. We have set up our differential equation as requested. Now we have to separate our variables. So that means everything with y on one side and everything with x on the other side. So this would become 1 over, or moving our y to the left hand side. So that's 1 over y. And there's the dy there. And then this should be equal to our k over x to the 3 over 2. And this is with respect, if we move this dx to that side, with respect to x. Okay, and so this is 1 over y dy, and then we're going to write our right hand side as k x to the negative 3 over 2 dx. And now we can integrate both sides, so that's the integral of 1 over y with respect to y. And then I'm just going to put the k outside of the integral sign since it is a constant. If we integrate our left hand side, we get ln y plus our constant of integration, and this is equal to k. To integrate x to the negative 3 over 2, we have to add 1 to our power. So this is times x. Negative 3 over 2 plus 1 gives us negative 1 over 2. And then we divide by this new power, which is negative 1 over 2, or just simply multiply by its reciprocal, which is negative 2. And this is ln y plus c is equal to, this is negative 2kx to the negative half. Okay, we can write this as ln y plus c is equal to negative 2k over x to the half, which is root x. Now, in the stem of the question, we are given coordinates that the curve passes through. We have 1, 1 and 4e. So let's use those to evaluate our constants c and k. Okay, so let's do 1, 1. So this would be ln 1 plus c is equal to negative 2k over root 1. So ln 1 is 0, and so we end up with c is equal to negative 2k over root 1, so that's simply negative 2k. And then now let's evaluate at 4e. So this is ln y. Y in this case is e, so that's ln e plus c is equal to negative 2k over root 4. So ln e, the e and the ln will cancel out and you remain with a 1, plus c is equal to negative 2k over root 4. Root 4 is 2, so that's 1 plus c is equal to, cancel out the 2's, negative k. Okay, so we now have two equations in terms of c and k. So here we already have c as the subject of the formula, so we can simply substitute it into this equation. So it becomes 1 plus c. C is minus 2k, so 1 minus 2k is equal to minus k. And now let's make k the subject of the formula. So that's 2k minus k is equal to 1. So k is equal to 1. Now let's evaluate c. C is equal to negative 2 times 1. So c is equal to negative 2. So if we substitute back into our equation here, we'd have ln y plus c is -2, so that will be -2 is equal to -2 times k, which is 1 over root x. Okay, so this is ln y minus 2 is equal to -2 over root x. Okay, now do they ask us to express y in terms of x? Yes, they did, expressing y in terms of x. So that means we have to make y the subject of the formula. So this would become ln y is equal to 2 minus 2 over root x. And if we apply the exponential to both sides, this would be y is equal to e to the 2 minus 2 over root x. And this would be our final answer. Part B. Describe what happens to y as x tends to infinity. So if we look at the equation of our curve, let's just rewrite it. Y is equal to e to the 2 minus 2 over root x. We have this section over here. That is 2 over root x. That's the part that contains x. And we're told and we're required to find out what happens to y as x approaches infinity. So this would be 2 over root infinity. So root infinity is a very large number. In fact, it's so large that we still regard it as infinity. So this would be the same as 2 over infinity. And we know that if we're dividing by a very large number, you can try it out on your calculator, you end up with a very small number that is very close to 0, such that we approximate this to be 0. So what happens to y as x approaches infinity is that y now becomes e to the power 2 minus this part that we have highlighted over here approaches 0. So y approaches e to the power 2. So we can conclude that, therefore, as x tends to infinity, y approaches e to the power 2. And this would be our final answer. So that's it for the differential equations video. See you in the next one. Welcome to the complex numbers video. This is the final video of our PO3 crash course. If you've made it this far, congratulations. Let's dive right in. The complex number u is defined by u is equal to 7 plus I over 1 minus I. Part A, express u in the form x plus iy, where x and y are real. Okay, so we're given that u is equal to 7 plus I over 1 minus I. So this is simply division of complex numbers. Okay, so let's extend this line over here. We're going to multiply both the numerator and the denominator by the complex conjugate of our denominator. So that means we're multiplying by 1 plus I. Okay, so that would be 7 times 1, 7, then 7 times I, that's 7i, and then we've got I times I, then we've got I times 1, which is I, and then finally we have I squared, that's plus I squared, and this is over. On our denominator, we have a difference of 2 squares, so that would be 1 minus I squared. Okay, and if we simplify this, we've got 7 7i plus I will give us 8i, and then I squared is -1, and this is over 1 minus I squared is -1, so this would be 7 minus 1, that's 6, plus 8i over 1 minus 1, that is 2. And if we simplify that, distribute the denominator, you've got 6 over 2, which is 3, plus 8 over 2i, which would be 4i. So that means that therefore u is equal to 3 plus 4i. And this would be our final answer for part A. Part B. Show on a sketch of an Argan diagram the points A, B, and C, representing U, 7 plus I, and 1 minus I, respectively. Okay, so if we sketch our complex plane, we've got our imaginary axis, and then we've got this would be our real axis. Okay, so our first point A is representing U, and we said U is 3 plus 4I, so that means we're moving 3 units in the real axis. Let's say that this is 1, 2, 3, so that will be 3, and then 4 units in the imaginary axis, 1, 2, 3, 4. So that means our point, this is point A, will be over there, and then we've got a point B. Point B is representing 7 plus I. Okay, so 7 plus I, that's 3, that's 4, that's 5, 6, 7. So that's 7 units in the real axis and 1 unit in the imaginary axis. So this would be point B. And then finally, we have a point C representing 1 minus I. Okay, so 1 minus I, that's 1 unit in the real axis, and then minus I, that's negative 1 unit in the imaginary axis. So that means our point C would be over here. That would be C. And this would be the Argan diagram representing the points A, B, and C. Okay, part C, by considering the arguments of 7 plus I and 1 minus I, show that arctan of 4 over 3 is equal to arctan of 1 over 7 plus a quarter pi. Alright, so the way we can get this, okay, so we can get this by saying that the argument of 7 plus I over 1 minus I, which is U, is equal to the argument of 7 plus I minus the argument of 1 minus I. So argument of 7 plus I over 1 minus I, that's the same as the arg of U, and this should be equal to arg 7 plus I minus arg 1 minus I. Alright, so let's evaluate arg U. We know that U can be written as 3 plus 4I. So U arg U would be equal to, since we have 3 and 4, that would be arctan of 4 over 3. And this is equal to arg 7 plus I. So to get arg 7 plus I, that is arctan of 1 over 7. Okay, so we have this minus sign over here, minus, and then since 1 minus I lies below the x-axis, to get our argument, we're going to say minus arctan of 1 over 1, which is simply 1. So this is arctan of 4 over 3 is equal to arctan of 1 over 7 minus arctan of 1. If you punch that into your calculator, you get pi over 4, or a quarter pi. And if we evaluate that, what we end up with is arctan of 4 over 3 is equal to arctan of 1 over 7 minus, which would be plus a quarter pi. And this would be our final answer. We have proved what they wanted us to prove. On a sketch of an Argan diagram, shade the region whose points represents the complex number z, satisfying the inequalities modulus of z is greater than or equal to 2, and the modulus of z minus 1 plus I is less than or equal to 1. Okay, so we've got the modulus of z is greater than or equal to 2, and then we have the modulus of z. I'm just going to factor out a negative sign here, so that will be 1 minus I is less than or equal to 1. Okay, so let's start by drawing this inequality over here. So we've got our imaginary x's, and then we've got our real x's. So this is the real x's, this is the imaginary x's. Okay, so this inequality over here represents a circle with the center 0, 0 and a radius of 2. So if I can draw that over here, that will look something like, okay, and then for this inequality, that's the modulus of z minus 1 minus I is less than or equal to 1. This is a circle with center 1 minus I and a radius 1. So let's draw that in red. So 1 would be over here, and then minus I would be over here. So that means our center of the circle is over here, and then it has a radius of 1. So let's draw our circle. Okay, so this is our circle. Now we have to figure out what our inequalities are saying. We have modulus of z is greater than or equal to 2. Okay, let's use a different color. Greater than or equal to 2 means we want the region outside our blue circle, which is the bigger circle. So the region outside the blue circle. And then this second inequality here is saying less than or equal to 1. So we want the region that is inside the red circle. So we want the area outside the blue circle, but it's inside the red circle. So that's this region over here. And that would be the shaded region that we're looking for. And that's our final answer. Solve the quadratic equation 1 minus 3iz squared minus 2 plus iz plus I is equal to 0, giving you answers in the form x plus iy, where x and y are real. So to solve our quadratic equation, we're going to use the quadratic formula, and a is 1 minus 3i, so 1 minus 3i, b is negative 2 plus I, b is equal to negative 2 plus I, and then c is equal to, that's I. Okay, so z is equal to minus b, so that will be 2 plus I, plus or minus the square root of b squared, so 2 plus I squared, minus 4a, which is 1 minus 3i, c, which is I, and this is O over 2 times a, which is 1 minus 3i. Okay, so this becomes z is equal to 2 plus I plus or minus the square root of, let's expand, we've got 2 plus I squared, so that would become I squared plus 4i plus 4, and then we have minus 4 times I times 1, so that's minus 4i, and then we have minus 4 times negative 3i, which is 12i times I, so 12i squared, 12i squared. Okay, and this is all over, that's 2 times 1 minus 3i, and so z is equal to 2 plus I plus or minus the square root of, wherever there's an I squared, replace it with negative 1, so that's negative 1, and then this 4i will cancel out with minus 4i, and so what we end up with is plus 4 plus 12 times negative 1, and this is all over 2 times 1 minus 3i, and so z is equal to 2 plus I plus or minus the square root of, so we have 4 minus 1, which is 3, minus 12, which is minus 9, and this is all over 2 times 1 minus 3i. So this becomes z is equal to 2 plus I plus or minus the square root of, we can write negative 9 as negative 1 times 9. and this is over 2 times 1 minus 3i, and so z is equal to 2 plus I plus 9. And because we've written negative 9 as negative 1 times 9, this allows us to then distribute the square root sign so that this is root negative 1 times root 9. And this is all over, that's 2 times 1 minus 3i. And so z is equal to 2 plus I plus or minus root negative 1 is I, and then root 9 is 3, so that's 3i over 2 times 1 minus 3i. Okay, so now let's write this as two separate equations. So we've got z is equal to 2 plus I plus 3i, and this is over the 2 times 1 minus 3i, and then we've got z is equal to 2 plus I minus 3i, and this is over the 2 times 1 minus 3i. Okay, so if we simplify, this would become 2i plus 3i, that's 4i, and this is over 2 times 1 minus 3i. So if we factor out a 2 in our numerator, that's 2 times 1 plus 2i, and this is over 2 times 1 minus 3i, and so we can cancel out the 2, so what we have is 1 plus 2i over 1 minus 3i. So they want their answers in the form x plus iy, which means we have to carry out division of our complex number. So that's multiplying by the complex conjugate of 1 minus 3i, so that's 1 plus 3i, 1 plus 3i. Okay, so if we simplify this, this would be 1 times 1, so that gives us 1, and then we've got 1 times 3i, that's 3i, 2i times 1, that's 2i, and then we've got 1 times 3i, that's 3i, plus 2i times 1, that's 3i plus 2i, so 5i, and then 2i times 3i, that gives us 6i squared, and this is over. Our denominator is the difference of two squares, so that's 1 minus 9i squared. So what we have is 1 plus 5i. Wherever there's an I squared, replace it with negative 1, and this is over, that's 1 minus 9 times negative 1. And if we simplify, we've got 1 minus 6. 1 minus 6 would be minus 5 plus 5i, and this is over 1 minus 9 times negative 1. So that's 1 plus 9, which is 10. And so this would give us negative 5 over 10, negative 5 over 10 plus 5 over 10i, and that would simplify to give negative 1 over 2 plus 1 over 2i, and this is one of our solutions. Now let's find the other solution here. So this is z is equal to 2i minus 3i is minus 2i. Okay, so let's just factor out the 2 instantly. So that will be 2, we had 2 minus 2i, so that's 1 minus I, and this is over 2 times 1 minus 3i, so the 2 would cancel out, and then what we end up with is 1 minus I over 1 minus 3i. Okay, and so we have to express this in the form x plus iy, so we're multiplying by 1 plus 3i. Okay, that's 1 plus 3i. So we've got in the numerator 1 times 1, and then we have 3i minus I, which is 2i, and then we have negative 3i squared. In our denominator, we have a difference of two squares, which is 1 minus 9i squared. And wherever there's an I squared, replace it with a negative 1. So you end up with 1 plus 2i minus 3 times negative 1, and this is over we evaluated this over here to become 10. So that would be, in our numerator, we've got 1 minus 3 times minus 1. So that's 1 plus 3, which is 4. So that's 4 plus 2i over 10. And if we distribute the denominator, we have 4 over 10 plus 2 over 10i. And if we write this in its lowest terms, that would be 2 over 5 plus 1 over 5i, and this would be our other solution. Okay, so let's move on to the next question. The complex number u is given by u is equal to 10 minus 4 root 6i. Find the two square roots of u, giving your answers in the form a plus ib, where a and b are real and exact. Okay, so we are looking for the square root of 10 minus 4 root 6i. So we know that the square root of a complex number is also equal to a complex number. Okay, so what we're going to do is we're going to square both sides to get rid of the square root sign. So this would become 10 minus 4 root 6i is equal to a plus ib squared. And so 10 minus 4 root 6i is equal to, now let's expand this bracket over here. That is a squared plus 2abi plus I squared b squared. So this is 10 minus 4 root 6i is equal to a squared plus 2abi plus, we know that I squared is the same as -1, so -1b squared. So we can write this as 10 minus 4 root 6i is equal to a squared over here minus b squared minus, that's a b, not a 6, b squared plus 2abi. Okay, and now we're going to compare the real parts on one side to the real parts on the other side, and the imaginary parts on one side to the imaginary parts on the other side. So we've got 10, that's the real part on the left hand side, and then a squared minus b squared is the real part on the right hand side. So we've got 10 is equal to a squared minus b squared, and then we have the imaginary part, -4 root 6. We don't have to include the I. -4 root 6 is equal to 2ab. So now we have two equations in terms of a and b, and we can solve these equations simultaneously to evaluate a and b. Okay, so let's make a the subject of the formula here. You end up with -4 root 6 over 2b. So a is equal to, that is -4 over 2, so that's -2 root 6 over b. And we can substitute this into this equation. So that's 10 is equal to a, which is -2 root 6 over b squared minus b squared. So 10 is equal to, if we square our numerator, we end up with 4 times 6, and our denominator would be b squared minus b squared. So this is 10 is equal to 24 over b squared minus b squared. We'll multiply through by b squared to get rid of our denominator. So that's 10b squared is equal to 24 minus b to the 4. And now let's put everything on one side. So that's b to the 4 plus 10b squared minus 24 is equal to 0. And we can solve our hidden quadratic. So that's b squared is equal to 0. And we can use positive 12 minus 2. And so b squared is equal to 2. And we have b squared is equal to -12. Okay, so now let's evaluate b. So here b is equal to, if you take the square root of both sides, plus or minus root 2. And then here b would be equal to plus or minus root -12. Note that in the stem of the question, they have mentioned that a and b are real. So it means that over here, we've got the square root of -12. We know that this will result in an imaginary root or an imaginary number. So we disregard that solution since they've told us that a and b must be real numbers, not imaginary numbers. So we stick to b is equal to plus or minus root 2. Okay, so now we're going to use this to evaluate our values for a. So we said a is equal to -2 root 6 over b. So we've got at b is equal to root 2, at b is equal to root 2, and then we have at b is equal to negative root 2. So here a would be equal to -2 root 6 over, that's root 2. Punch that into your calculator. It is -2 root 6 over root 2, and that will give us -2 root 3. And then at b is equal to -root 2, we have a is equal to -2 root 6 over -root 2, and this would give us a is equal to positive root 3. And we can conclude that our two square roots are, here our a is -2 root 3, and then our b is root 2, so that's plus root 2i, and then here our a is 2 root 3, 2 root 3, and our b is -root 2, so -root 2i. These are the two square roots of u, and this is our final answer. This also happens to conclude our Pure 3 crash course. So this is it for our crash course, and I wish you all the best in your exam. Bye bye.